Good morning. Okay, back to discrete optimization, local search. And so far, one of the things that we have done is looking at all these neighborhoods. And, we saw a variety of them, some from very simple to very complicated one. What we want to do today is step back a little and actually look at how we search these neighborhoods. Okay, so we have talked about the neighborhood, but not really how we use them for searching. It was very implicit. So what we want to do in the next 3 lectures is take a systematic look at how we can exploit these neighborhoods and do local search on top of them. Okay, so more systematic presentation, and then we're going to, study heuristic and meta-heuristics. Okay, and so that's going to be a focus of essentially the lecture today and the next 2 lectures. So today mostly heuristics, the next 2 lecture meta-heuristics. Okay, so remember, local search work with states. Okay, at any point we are in the states. It's either a solution if we only explore, feasible configuration, or it's a configuration where there may be violations. Some of the constraints are violated. Okay. Now, essentially, the local search is going to move from states to states. Okay, and essentially, from one state, you can only move to a subset of states, which are called the neighborhood. Okay, of that particular state. So we're going to use the function ns to denote the neighborhood of state S. That's all the other states that you can reach when you are at S. Okay? Then we're going to introduce this legal function, which basically tells you, from all these neighbors that you can go, which ones are legal and which ones are not to move. Okay, so there will be a subset of the states that you can move to. Other ones, you will be basically preventing the search from going there. Okay, so this has kind of been implicit in what we have done before. Okay, so always moving to something which is a better place. Okay, but we'll see many other ways to do that in this next 3 lectures. Okay. And then once we know which neighbors are legal, what we're going to do is select one of them. And once again, there will be many, many ways of actually selecting the neighbors. Okay, so what you get is this crazy function, S of L of N of S, and then there are all the other S's that you can use in the other function. But essentially what you do, you select a legal neighbor, okay, from the state you are in. Okay, so the algorithm, and of course what we want to do is obviously in some cases minimizing an objective function. Almost always either it's minimizing violation or it's actually optimizing an objective function from the problem specification. Okay, so this is the general pattern that we are going to use in the next couple of lectures. Okay, so you have the local search, you have the objective function f, you have the neighborhood n, and so we'll give you a definition of that. We'll pass that to the local search. You have the function L and you have the function S for which neighbors are legal, and then what is the selection function. Okay, and most of the local search, we'll adapt this a little bit from time to time, but most of the local search are going to start from a configuration that you generate, and you can have different ways of doing that. And of course, that's the best solution you have at that particular point. So S star is like keeping the best solutions at this point of the search. And then you're going to do a number of iterations. Every one of them is going to go to a neighbor and so on and so forth. Okay? And obviously, if the neighbors is satisfiable and it's improved the current best solution, you have found a better solution. We have found a better solution and we store it. And otherwise, what do? We move to the next neighbor. And how do we do that? Well, basically, we select a legal neighbor in the neighborhood of S. Okay? So, and at the end of the search, we return the best solution we have found. Okay, so this is the schema that we're going to use. And one of the goals today is to give you some example of what L can be, of what S can be, of what, and mostly we have seen what the neighborhood can be. Okay, and so that's the goal. The goal is to look at this L and S function, and so all the variety of things that we could do there. Okay, so this is an illustration, graphical illustration of what we do. So we start at a particular state. Okay, over there. Okay, and then essentially what we're going to do is define the neighborhood of that stage. So this is the regions that you see here. That's all the neighbors. Okay, so potentially we can move to all of them. But then we put this restriction. Okay, so I only want to look at these neighbors which satisfy this legal condition. And now you see all these 3 neighbors there in this particular case. And then we select one of them. This is, the selected neighbor. Okay, and then we move. Okay, and so now we have moved from, the original node to the selected node. Okay, we restart the process. These are all the neighbors. Okay, some of them are legal, some of them are not. Okay, and then you select one of them. Okay, so here, and then you move to that place, and you continue doing that, and you see the search moving all over the place until it reaches the final state. Isn't that beautiful? We have to do it again. I mean, it's so beautiful. You can't imagine how much time we spend doing this. So I want to show it again. So we start from this. We select the neighbor. okay? The legal ones, we move, okay? We redo the same thing, we select the neighbor, the legal ones, we move, okay? And then we keep moving, okay? And so this is essentially what we're going to do today, okay? Looking at not the neighborhood because we have already seen many of those things, but looking at what this legal function is and how we select a particular neighbor, okay? And there are many, many ways to do this. People are really creative in this field, okay? So, for instance, one of the things that we have seen so far many, many times is only looking at local improvements. When you are in a state, you only want to move to another state, and in this particular case, which is better than the current state, okay? So you always want to improve, okay? In a sense, you always want to go up, 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 okay? Better and better. Actually, we are minimizing, so down, 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 okay? So, and then the selection function, many times what we have done is looking at something which is greedy. You look at all the neighbors that are improving and you take the best one, because somehow, you believe that this is going to give you the best solution quickly. Okay? So these two things are things that we have seen, kind of implicitly so far. Okay? Now, in this field, okay, in local search, we typically distinguish between heuristic and what is called meta-heuristic. Okay? So one of the things in optimization that you have seen so far, right, is that we are always very good at choosing nice names, like heuristic, meta-heuristic, and you'll see many of very fancy names today. Okay? So we are very creative people. Okay? A heuristic is something that essentially tells you how to choose the next neighbor. Okay? It's basically telling you, okay, this is the heuristic, this is the way you want to choose the next neighbor to go to, okay? And typically you use only local information, the state S at which you are, and then the neighborhood, obviously. Okay, and the goal of this heuristic is essentially to drive you down to a local minimum, okay? To a local minimum, a good one, or hopefully. Okay? Now the meta-heuristic is a little bit different, okay? So the goal there is going to be escaping local minima, okay? So if you only do local search, let's say using greedy improvement, you're going to get to a local minima. Most of the time, you have no guarantee on the quality of it. Okay? So the meta-heuristic is going to say, oh, I'm stuck here, but I want to try to get out of there and see if there are other local minima that are good. Okay? So that's what you're going to do. Okay? So essentially what you want to do is use the meta-heuristic, and we'll see a bunch of them, right? We'll see how they can drive the search out of local minima and trying to get closer to the global optimum by using kind of non-local information, okay? So what typically these things have, they have some kind of memory or some kind of learning component, okay? And so this is essentially what the difference between these two things. One of them is going to guide you towards a local minima. The other one is going to try to allow you to escape from the local minima and tries to get to global optimality. Okay? And so today we're going to talk mostly about heuristics, and then we'll spend the next 2 lectures talking about meta-heuristic. Okay? So one of the ways that you define legal moves, okay, and that drives also the heuristic, is by looking at condition of the objective function. There will be other things that we are going to look at, and you'll see some of them today and in the next lectures. But essentially, what I'm going to show you now are just condition of the objective function. Okay, so local improvement, we already mentioned this. Essentially, you want a state such that you improve the value of the objective function. Okay, so that's a strong condition. You have always to move to some place which is better. Okay, now sometimes there is no such neighbor, but there are neighbors that are different from where you are. Okay, obviously, and these neighbors may not be better than the current state, but they can be equally good. And so it may still be advantageous to move there because maybe from there you can move to a place which is better, okay? So that's called no degradation, essentially. And what you do is you basically select something which doesn't degrade the value of the objective function, okay? So very useful in many conditions, okay? And you can also use that to introduce randomization, and we'll talk about that a little bit later, okay? And then you can be completely, brutal and say, I can consider all the neighbors, okay? So, and we'll see some search heuristics here that will actually do that. Okay, and so essentially, potentially everything is a neighbor. Okay, of course we're gonna, once you have something that consider everything, you will have to have a selection function that does the right thing. Okay, so it's going to be a combination of what is legal and how the selection function works. Okay, so but these are some kind of properties of what you can do. Okay. So now you have also one of the things that you will have to see is that you will have to, once you have the neighborhood and once you define what is legal, you will have to decide how to explore this neighborhood, okay? And sometimes the neighborhood is tiny, sometimes it's huge. So the way you explore this neighborhood is important, okay? So we'll see various kinds of things, okay? So one of them is best neighbor. You want to look at the neighborhood in its entirety, and you want to select the best neighbor. A lot of local search are doing things like this, but of course that means that you have to scan the entire neighborhood neighborhood and select for selecting the best neighbor. Okay, but this is one of the things that is very popular. Okay, the next thing which you can do is to say, oh, I'm not interested in exploring the entire neighborhood. I want to stop as soon as I find something legal. Okay, and sometimes we call that the first neighbor. Okay, so you want to find something which is legal, and then that's sufficient. You stop at that point. The hope is that you don't have to explore the entire neighborhood. You can very quickly find a neighbor that is legal, and then you move there, and then you start. Of course, when you at some point you will have to explore the entire neighborhood to find out that there is nothing legal. But in a sense, most of the time you hope that you will only explore a subset of the neighborhood. So if the neighborhood is big, you can still use something like that. It would take more time if you try to do the best neighbor. And then we have this thing which is called multistage selection. And the key idea there is that you want to preserve some of the greedy aspect. That's really important for you, but you don't want to explore the entire neighborhood because it's very big. So what you do is you basically split the neighborhood exploration in two parts. The first one is going to select part of the neighborhood, so you won't explore the entire things. You will only select a sub-part of it. And then the second part is going to explore in its entirety the rest of this sub-neighborhood. Okay? And I'm going to give you an example of this because this is very interesting and very useful in practice. Okay? Now let's talk a little bit about the best neighbor. Okay, so in practice, you may have many different neighbors that have the best value. Okay, and in those cases, randomization is very important. So you don't want to be, in many cases in local search, you don't want to be completely deterministic. You want to introduce this randomization component, and that allows you to explore the search in a more, in a more interesting fashion. Okay, so we'll talk about this much more at some point. But at this point here, considering the best neighbor, there is something very easy to do. Okay, so you basically take all the best neighbors. So these are really the legal moves that you want to go, and then essentially you want to select one of them, but you want to do that randomly. Okay, and so what you do is if they are essentially if the number of neighbors is cardinality of n and star, which are the best neighbors, you want to select one of them with a probability which is 1 over the size of those best these best neighbors. Okay, so in a sense what you do here is you compute all the best neighbor, and then you basically choose one of them in a uniform random fashion. Okay, and so we often do things like this because it gives you ways to actually not going always to the same place, but it gives you more variety. Okay, so essentially when you see best improvement, you can parameterize the local search that I've shown you at the beginning by simply using essentially using improvement as the legal moves, and then selecting the best one. Okay, so if you select these things, you have a local search. The legal moves are going to be the one where you improve the value of the objective function, and then you always select the one which has the best value with the definition that I've given you here, which basically means you compute a set and then you choose one of them randomly. Okay, so that's one of the things. So you could do similar things for the first neighbor. In that particular case, what you do is essentially you take the first neighbor in the neighborhood, exploring it in some kind of lexicographic order, okay, and that's what you return. Okay, and so once again, the function can be very easily computed. What you do is you say, oh, the legal moves are the ones that improve the objective function at the current state, and then you want to select the first one which is legal in a sense. Okay, so that's how you can parameterize the search, the generic local search that I gave you before. Okay, so let me talk a little bit about the multistage heuristic because, as I said, some of them are really useful in practice. And the motivation, as I said, is you still want to keep the greedy aspect, but you don't want to scan the entire neighborhood because for some reason it's too large and it's not a good compromise between, the quality of the solution and the efficiency of the algorithm. Okay, so we have seen one of those. Okay, so one of them was essentially the way we did the search for the queen's problem. Remember when we did the queen's problems, every queen could be associated with a violation. That's the number of other queens that the queen is currently attacking. And then we were basically looking at that, queen that is the most aggressive, right? And we were basically moving it to a position where it was much less, the least possible, aggressive. Okay, so basically the position where which minimizes the number of violations. Okay, so what we did was two-step, right? So we selected only one queen, and then we moved this value to its best position as far as decreasing the violations are concerned. Okay? So in a sense, this heuristic is sometimes called max-min conflict. You select a variable which appear in the most violation. It's greedy. Okay? It's a greedy choice of the variables. And then you select the value for that queen, so a row, okay, for the column of the queen, okay, which result in the smallest number of violations. Okay? And that's also a second step which is greedy. But the first step is already selecting one queen. Okay? So in the second step, we only look at one queen, not all the queens. Okay? Now, a variation on this is the original min conflict heuristic that was proposed by Steve Minton. And what you do here is you just select the first queen randomly. It has to have some violation, but you select it completely randomly. Okay? And then you select the value for that queen, which minimizes the set of violations. So that's typically called the min conflict heuristic. So the first step is randomized. The second step is greedy. So these are two examples of multistage heuristic. You first select some part of the neighborhood, a queen, and then you look at all the possible values, and you select the one which is the best in the second stage for that particular selected queen. Okay? Now, what would be the alternative to that? The neighborhood that you could explore are all the queens and all the possible moves for these queens. So you would have a quadratic neighborhood, okay? And the stack state, okay, the set of state would be obtained by looking at the current state, taking any queen q and any value v, and looking at what that state result into. Okay? And the key point is that when you do that, you may have solutions that are actually better than what I've just shown you, right? It's not necessarily the queen which has the most violation, which is going to decrease the violation the most. It may be a queen which has fewer violations, but then you can reduce the number of violations tremendously. Okay? So that's basically, this is a quadratic neighborhood. It would give you the best local move. What we do is an approximation of this, right, by using essentially a first selection of the variables and then a selection of the value, instead of considering the entire thing globally. Okay, so the complexity here would be quadratic. Okay, all the pairs for all the columns and the rows. Okay, so and therefore there is a price to pay here. It's essentially you are proportional to the number of tiles in the chessboard. Okay, when we look at the min conflict of the max min conflict heuristic, this is a neighborhood which is explored in linear time, right? So we basically select a queen. Okay, that may take at most linear time. In min conflict, it's constant time, and then you have to select the value, which is also looking at all the values, right? All the values in the column, that's linear time. So, constant plus linear or linear plus linear, it's linear time. Okay, so what you see here is a trade-off. Okay, so we won't have the best neighbor, but we'll have a kind of a greedy neighbor anyway, but we take only linear time instead of quadratic time. So we can explore many, many more neighbors in a sense. Okay, and so this is the kind of trade-off that you often have in local search. Okay, and these multi-stage heuristics, as I said, are useful. Okay, very useful. Okay, now think about it. We also saw the car sequencing example, and remember we had all these cars on this assembly line. There were constraints on how many units how many cars, how many options a production unit could put on a car. Okay, in a row. And then essentially we were basically scheduling all these cars on the slot, okay? And the stars here are all the cars that are basically violating some of these capacity constraints, okay? And the neighborhood we selected was, we want to take two cars, one of which has to be in violation, and we would just swap them. Okay. Now, if we want to have a completely greedy procedure, okay, for this particular neighborhood, okay, so it's going to be a quadratic neighborhood, right? So we can scan every slot in the assembly line and then swap it with all the other slots in the assembly line, and that's a lot of swap, right? So if we have an assembly line with let's say 300 cars, this would be exploring about 45,000 configurations. So it's going to take a while to do that. Okay, so a multi-stage neighborhood would just say, I'm going to select one car. Okay, so it's kind of a linear scan of your assembly line. Okay, and then you're going to see, which other cars can I swap it? Another linear swap of the neighborhood, and that's essentially a much smaller neighborhood, right? It's like 600, at most 600. Operations that you need to do. So it's linear in the size of the assembly line. So once again, you have this trade-off here. I can get the best move, or I can get a very good move, but much faster. Which one is the best? Well, that will depend on the problem, but you have to consider these options when you're designing a local search procedure. Okay? So that's, to give you a sense, you can take the best neighbor, you can take the first neighbor, you can take something which is in between in a sense, which is, taking something which is greedy, but with a multi-stage approach. So what I want to talk about now is random walk, which is a completely crazy idea in a sense, but there are applications where this is really the thing to do. Okay, so randomization is what? You want to select a neighbor completely at random. Okay, and then you have to decide whether to accept it. Okay, and so some of them are going to accept the move if it's improved, or you can use the Metropolis algorithm that I will talk about, later on. Okay, but essentially what you're going to do is select a neighbor randomly and then decide if you accept it using some kind of criteria, right? And so essentially, let's look at the first one, which is random improvement. What you do here is that you basically look at the neighbor, okay, the entire neighborhood, and you take one neighbor with, some probability, which is essentially you assume that all the neighbors can be selected with the same probability. You take one randomly, completely randomly, and then you look if it improves the current solution. If it does, you move to it, okay? If it doesn't, you stay in the same state, and you iterate these things, okay? So this can be actually very effective, okay, in some particular kind of local search, okay? And there are various cases where this is effective. And one of them is when the neighborhood is really, really large. Okay, so remember this traveling tournament problem? Okay, so we had all these teams, kind of the baseball teams, that had to meet with, play against every other team twice. It was a round-robin tournament, and so you would play some games at home, then move, play some games away, then come back and play these things. And the goal was to minimize essentially the travel distance. And so you had these constraints, making sure that the team don't play too many games in a row at home or away. And then you have basically this optimization, this objective function which was global and therefore difficult to optimize. Okay, and so what we saw is that there were plenty of moves that we could do, right? So we could swap home, swap teams, swap rounds, and then the partial version of these guys. Okay, and some of these neighborhoods are actually pretty complicated. They are, let's say n cube moves in some of these neighborhoods where n is the number of teams. Okay. And more important, equally important in a sense, some of these moves were affecting the entire schedule. So you had a lot of operation to carry it out. Okay, so this was essentially swapping the teams here, and so you would affect, a large part of the neighborhood there, and then you had to flip some of these to restore feasibility. And so what you see here in color, essentially, are all the things that have been moved during that have been changed in that particular move. So when you look at something like this, you have many, many, many neighbors, and every one of them is going to affect the entire schedule, so they take long to evaluate. So you just can't really do very effectively a best neighbor, a best neighbor exploration, because that would take a lot of time, and the benefits are not really very clear at that point. Okay, so what you can do instead is just select one of these moves randomly, see if it improves your schedule. If it does, yes, you take it. If it doesn't, you just stay in the same state, pick another one, and so on. Okay, so the best results that I've shown you when we talked about the TTP, the traveling tournament problem, were based essentially on a random walk. And I will tell you also what is the meta heuristic and what is the heuristic to decide whether we accept a move or not. But it was basically using completely random move at every iterations of the search. Okay? So this is essentially the high-level presentation that I wanted to give you today. So we saw essentially the generic search and how you can parameterize it with heuristic and meta-heuristic, but I haven't shown you the meta-heuristic yet. And that's what we're going to talk about next time. Okay? See you next time. Thank you.